I've been a product manager for TotalView for not all of the years it's been around. I think it's been developed for about 20 years. I've been the product manager for the last 7 or so. One of the things to be aware of is I'm the person at RogueWave who's responsible for figuring out what we put in the product next, what we do, what we don't do with the product. And one of the big things is there's always more stuff to do than there's possibly hours in the day to do things. So one of the things that I really thrive on is feedback from audiences like yourself. And you can raise your hand as I'm talking and throw things out, or you can grab me by the collar, or just tap me on the shoulder or whatever during the lunch break or this afternoon, and give me feedback. I'd love to know if there's new things you'd like to see in TotalView, if you've had any problems, anything like that. I'll always do my best to chart the roadmap, but I can always do that better if I hear from you guys. So. Anyways, that's I guess one of the big inputs is don't be shy. Let us know what sort of challenges you have in troubleshooting and debugging codes, and we can always work to improve it. One thing to be aware of: RogueWave does a lot of other things beyond TotalView. We have a whole range of different software products that target HPC and also sort of commercial development. I won't run through the whole list because that would be boring, but you can check the website for that. One of the cool things that we just did as an acquisition recently is some I guess what I would describe as sort of hardcore static analysis for C++ codes. We acquired a company called Clockwork, and they'll go through and look at huge C++ applications and do interprocedural static analysis and find potential errors even just from looking at the code. And I think that complements really nicely TotalView. So TotalView is your dynamic debugging, sort of when the rubber hits the road, what is the code actually doing? And Clockwork can look at the code and sort of reason about it abstractly and find potential errors even without it running, and even in areas that aren't executed. So RogueWave in general is trying to bring together tools, components, libraries, and all kinds of different things that you might need to develop great code. I think the tagline these days is accelerating good code or great code or something. I'm going to talk about a lot of different stuff. Hopefully not too long about each individual thing. I'll do a little bit of an introduction. Then I'll talk about the TotalView itself. Give a demo, and I'm hoping to expand that. I think that'll be more fun, more interactive. And then I've got a large set of slides here on debugging MPI codes, and those are mostly for reference. I'll probably reference a couple of those in the talk. I'm going to focus a little bit on memory debugging. I think that's one of the things that TotalView really does well. I'm going to talk about debugging accelerators and coprocessors. I know Mira doesn't have those, but I think a lot of the future systems that people are looking at are accelerator or coprocessor based. And I was looking at the charter of this training, and it's supposed to set you guys up for the future. So I think it's worth mentioning those. We'll talk a little bit about batch debugging capabilities in TotalView. I'm going to talk about reverse debugging, which I think is a really neat, really differentiating thing about TotalView. It allows you to work sort of backwards. And I may actually do a little bit of that during the demo, just so you guys can see that. And then I'll close with a couple of tips on running on the Argonne systems. What do we see when we look at the market? Again, one of my challenges is to try and figure out what we need next. We see a lot of sort of changes and complexity that I think impact code. I mean, it's kind of being driven by the hardware side, but you guys have been spending this last week and probably a lot of time before that thinking about writing, probably, I'm going to guess, scientific codes to run on these big systems. And you have to think about, I think there's a lot of challenge. How do I architect my program? How do I kind of future-proof it for new technologies that are coming along? How do I get the most performance out of it now? How do I make it run at the right scales? And you're doing all that thinking in a world where there's like some pretty big technology changes going on with the GPUs, with the coprocessors. No longer can you just write a darn good MPI code. To somebody's question here, you have to write a darn good MPI code, then you have to add OpenMP to it, probably, or something similar. And meanwhile, you also have to be thinking about vectors. You have to be thinking about data movement, possibly back and forth between two different memory spaces on each individual node, and then all of that's got to be tuned and run correctly and quickly. So there's a lot of uncertainty, I think, in terms of what languages are coming along or will be successful in the long run. We can see what's here now, but which ones will be successful. So CUDA and OpenCL, OpenACC, OpenMP. Regardless of what happens, it seems really clear that core counts and thread counts and complexity is not going down anytime soon. So that's what I sort of see when I look out at the market. And I guess I have a lot of sympathy for you guys and everyone else who's developing software. It's not a simple world. Code that's run for a long time will probably continue to run, but if you really want it to run well, you're likely to be thinking about either re-architecting it or porting it or changing it in deep ways. So, and that's hard, right? Especially old code. If you're sitting down maybe as a newer member of a team or even someone who wrote the code ages ago, it's probably not fresh in your mind. You're probably going to be digging through and doing some almost, I hesitate to call any scientific application legacy, but sometimes we're dealing with the kind of challenges that in the business world gets called legacy application maintenance kinds of challenges. You know, older coding styles, dusty deck Fortran codes, and just, you know, the person who wrote the code may not be available anymore. So I think there's a lot of need. I don't think it's any more complicated than that. There's a lot of need for having good debugging tools available, and between TotalView and DDT and Tau and HPC Toolkit and all the other tools around, I would encourage you to try and use more than one. You know, build yourself a good experience base, a good toolkit with all the different tools that are out there, and then choose the right one for your needs in a given day. So what does RogueWave do to help with this? So we build TotalView. It's a troubleshooting and analysis tool. It's really home-based in HPC. So you know, it's back in the day when it was first developed by BBN. We were joking about before. The architecture that it was built for was the first distributed memory parallel program. It predates MPI by a long way, but it was the first architecture where someone was trying to build an application and a system that architecturally is like our clusters these days. So it was originally built to solve that problem. It gives you visibility into and control over concurrent parallel application. We have done a lot with scalability within TotalView. Now, that means we've sort of moved it up from, you know, 4 processes and 8 processes to hundreds of processes to thousands of processes to hundreds of thousands of processes. I'll talk about the architecture of TotalView here in a little while, but be aware that we see that as a really important goal for TotalView and kind of a constant challenge. Usability as well. TotalView, you know, doesn't matter if the tool is fast if you can't get the information you want out of it. You will see a lot of features and functions in TotalView. There's, for example, 3 or 4 different ways to get at variable data, and that's to give you a quick way to get a quick glance, a way to sort of dive deeply into data structures, a way to compare different data. All those things are available because you sometimes need one, sometimes you need the other. We try not to have one. We try to give you a range of different tools. We put a lot of advanced functionality in TotalView over the years, and I'll talk about some of it here. And of course, one of the big challenges is just keeping up with all the platform and language changes, and I think we do a good job of that, but it's definitely always keeps us busy. Okay, so what is TotalView? Again, it's a graphical C++, Fortran debugger for a wide range of different Unix-like and Unix systems. It works all the way from laptops all the way up to the biggest supercomputers, and it's really here to make your job as a programmer easier. Right? We're going to help you be more productive, have a lower stress level, be able to get off work more quickly, and go home and have fun. All those things. You know, no one wants to be at the office at 10 o'clock at night still debugging. or the lab or wherever, still debugging, or taking your computer home and setting it on the kitchen table while you're eating dinner, trying to debug things. So we want to help you be more productive. So it's a graphical user interface with strong data visualization. We focus on parallel debugging and support these different range of paradigms. One of the things that we really focus on in the architecture of TotalView is low resource usage. So we believe that the supercomputer that you're using, or whatever computer you're using, is mostly for your application. So we have chosen an architecture from the very beginning that is very lightweight in the memory usage and resource usage in the environment where your code is actually running. And that has that's definitely a factor about how TotalView works. TotalView does all the heavy lifting in the front end GUI that has very lightweight agents out in the cluster. And that's a different architecture than other parallel debuggers. That has definitely some advantages and some trade-offs. We'll talk about that in a few minutes. It includes a remote display client, which I'll demo here, which you can use to work anywhere. I'll show it connecting to over here to Argonne, but I could easily be connecting to Germany or wherever in the world, and it does a nice job of handling the transport so that works quickly. We have very powerful memory debugging. As John mentioned at the beginning, memory is very limited resource and seems to be architecturally, if you look at long-term trends, getting to be more and more limited. So I would not be surprised if some of you are thinking, okay, well, my code, I want to be very aware of how making a change in my code is going to impact the memory usage. So we have some great techniques and capabilities in TotalView to give you a sense of where your code is using memory, do comparisons and things like that. We have deterministic record and deterministic replay capability, replay engine that I talked about. That's x86 only because it's a low-level technology that's really just been implemented for that. It could theoretically work on power-based systems. It doesn't yet. But that's really cool. That allows you to sort of step backwards through code, and I'll come back again to that. Non-interactive batch debugging, and another thing that I'm not going to focus as much in this audience, but actually, let me ask. Hopefully, you guys don't mind me asking you to move your arms around a little bit. How many people here primarily write Fortran? Okay, that doesn't surprise me. How many people here primarily write C, C++? Oh, okay, well, maybe this is more important than I thought. So you guys are doing a lot of C, C++ stuff. Okay. How many people here use something other than those, like Python or something? Okay, cool. We don't support that in TotalView yet, but we do have a lot of customers who are doing Python codes that make calls down to, they use that for the sort of glue layer, and then they call down to Fortran and C. And that does work. Where there's some thought, we have some thoughts about how to make that a more painless process. But anyways, there's some. We put a lot of effort over the last few years to really handling. Sort of doing the heavy lifting to handle C++ well. So once you start writing in templates, a single line of code can translate to lots of locations in your application. And we don't think it's fair for the debugger to sort of punt that problem. And when you set a breakpoint on a templated line of code, you get a breakpoint in one of those templates at random. We don't think that's fair. So TotalView has a concept called closure. By default, you're going to get a breakpoint in every instance of that application, of that line. Regardless of all the different input types, and you can narrow that down if you want. So you might want to only look at some commonly used template function only for the new data type that you've added. So you can totally do that, and you can totally do that in a pretty direct way in TotalView. Or you might want to just look at anytime this line of code gets hit. So we handle both of those. We also do some great transformation functionality for either the standard list vect map kinds of things, or for your own objects. So you may have, and we have customers who have very complex C++ objects, and they're like, well, for troubleshooting, I really only care about these 3 fields, or I need to transform this in the same way that, from the spaghetti of pointers to something sensible, and we give you several powerful ways to do that. I wasn't planning to dive deeply on that, so I don't think I have a lot of slides on that, but given that you guys are mostly doing C++, that's good for you guys to be aware of. Okay? Okay, so talking a little bit about the architecture of TotalView. And And I'm just explaining this not because you should necessarily care, but so that you understand where TotalView is coming from and you understand some of the approaches and philosophies that we have at RogueWave about debugging. And I think it'll help when you're using the tool just to have a little bit of this in the back of your head. Okay, so we have a front end, and this is my idea of doing graphics. I'm horrible at doing visual stuff, so I accept 100% responsibility for how ugly this graph is. We've got marketing people who will make that pretty, and I've just never sent them this particular slide. I've used it for years. I think maybe I take a stubborn pride how ugly this graph. Anyways, the red things here are your code. They're the MPI programs running. You might have an MPI starter process here. You got your compute nodes out there, and you might have multiple different MPI ranks on each one of the compute nodes. That makes sense, right? That part of the graph makes sense. And then I drew TotalView in there in the kind of blue color, and I drew two different kinds of boxes for TotalView. The MPI ranks, they're about the same, on all the different nodes. TotalView, I drew a big fat TotalView here on the front end node, and then a little skinny TotalView out in the compute nodes. And that was on purpose, because I'm trying to highlight the idea that the TotalView debugging agents, which we confusingly call TVD servers for historical reasons, but they're really more agents than servers, run out in the cluster, and they're real lightweight. They never build any of the big fat data structures that you need to really understand your code, that the debugger really thrives on. We don't put one of those on every node, and we certainly don't put 10 or 16 or 32 of those on every node. We put one little agent out there. It talks to all the different processes, and then it talks back to the front-end version of TotalView, which has this, what would seem like it's crazily complex symbol table that understands all the different stuff that's happening, not just in one process, which is kind of complex enough for a debugger, but all your different processes. And it handles all the differences that might happen between different library load addresses and things like that. And it also handles, in a single symbol table, the fact that you might have different code versions running in different places. But we put all that complexity on the front-end node so that you can use all of the memory on the compute node. So what we want here is for this picture without the debugger and this picture with the debugger to be very similar, right? We're not using up a bunch of memory. We're not making it so you have to change your allocation or change your target program at all. We want to do as little Heisenbugging as we can, right? We want to make the tool play nicely with your code. Old school TotalView, and this is in transition. We're in a point where we're doing a lot of tuning and digging around in the internals of TotalView. Old school TotalView talked to each one of these directly. So that obviously creates a huge bottleneck, presents scalability challenges, and historically TotalView has taken a long time to maybe start up and to attach to all of the different processes. Because basically it's making it's kind of making a time-space trade-off. So we're doing more work in TotalView, in the internals of TotalView, to keep you from having to sacrifice a bunch of memory on your target process to do debugging. Does that make a little bit of sense? What we've been doing recently is, and I'm going to skip ahead a little bit, we've got a couple of big projects going on. Again, we have a 20-year-old code base, so we're doing some changes to improve the scalability and change that flat structure I just talked about to something better. And we're also doing some modernization of the GUI, which I will admit, in need of. And both those things are being worked through what we call early access programs. So you don't need to know that. I'm going to talk a little bit about the details here, but you don't need to know the details too much. But just know if you're interested in either of these projects, there is the opportunity for you to provide feedback and tell us, you're going the wrong way, don't do that, or you really need to do this. So please reach out to me and express interest in one or both of those if you are interested. So the scalability, again, sort of a fundamental challenge we have. Again, the client version of TotalView is doing a lot of the, all the knowledge about, for example, if you're stepping through your code, where are possible places your code might run to next. That analysis happens in the TotalView client, and that gets sort of passed out to the debugger servers, which again are kept lightweight and kind of simple. When you have 100,000 of these, 100,000 connections from one, and that's kind of going to be slow. So what we've done is we've changed the infrastructure of TotalView to provide to use MRNet, which I think some of the other tools in the space use. It's a University of Wisconsin thing. And so it's a sort of standard layering technology for doing this kind of thing. We've done that, but but the challenge is, and what this does allows us to send messages down the tree and then take reduced messages back up the tree. The challenge there, though, is that the smarts of TotalView still, for the most part, lives up here in the client. And so what we're trying to do is be very careful and think about each individual operation and decide in what cases does it make sense to move parts of the smarts of the debugger down into the tree. So we preserve this fundamental architecture we've talked about, which is lightweight on the debugger servers and keeps the smarts out of the cluster. So for us to do the scalability has been a challenge of going through each individual operation and optimizing it sort of separately from the others. So we're getting to some of the same scales as DDT is with the debugger, but we're doing that inside the debugger rather than just having a wrapper around a bunch of GDBs. So that is where we're at. A few years ago, we did just a run just to sort of prove this out. We've got our partners at Livermore to, they were kind enough to give us a little bit of time on half of Sequoia, and we ran TotalView successfully at half of the machine scale. Okay, I mentioned this project is so that was just to prove that the architecture works. We can scale to that level. TotalView doesn't fall over, et cetera. The other thing one of the other things we're doing in there is working on changing the way we display data. So this shows, for example, it's actually an older version of the root window, which shows how we're pulling things together. Basically, the older version of TotalView would give you a list of things, and from a GUI perspective, lists fail at hundreds of thousands. They're just not useful. So this was actually a first step. I'll show you a demo later on that'll do a newer version, a nicer version of that. We're getting away from that list syntax to a more compressed syntax to express, for example, the status of different processes. This shows that same sort of functionality happening in the call graph in TotalView. So you can use this kind of display to see where your program is in a large application. It's very similar to the stat tool, again, from Livermore. Again, this is in early access. You can turn that on. In general, in TotalView, by turning on these two different flags, if you have the scalable early access version, and I'll give you some instructions later on for how to do that. You will have access to this scalable early access during this class and this evening if you want to. And I've actually got a simpler way to do it than this. I'm going to show, which way do I drag here? Okay. So I've got, this is our remote display client that I mentioned earlier. This is the best way, I would say, for you to connect TotalView to your desktop for debugging. It's very simple. I've just typed in the machine I want to log into, my username there. On the advanced options, I can save myself one login by pinning my display number. If you don't have to put this in, but if you don't, then TotalView will, or the remote display client will log in once and try and figure out what is a free port, and then it will log back out and log back in with the port that it's figured out. But you'll have to log in. You'll have to type in your password if you have to do that twice. So let's skip that. We just picked one that we know is free. And that's all I have to set. I don't have to set anything else, assuming that on my machine I'm logging into, I have TotalView in my path. And that's as easy to do on these systems here at Argonne as just in your .soft file, just add plus TotalView. And then you're good to go. You got the right path. So if I just hit Launch Debug Session. Oh, this has popped up over here. I'm not used to doing this on two windows. I apologize. It's popped up my login prompt. I'll try not to say this out loud as I type it in. OK. And what we're doing here is it's setting up a remote frame buffer style window to Vesta. This is what that window looks like. We're using a simple window manager called TWM, which you might remember from the 80s or 90s. But the nice thing about it is it's tiny. It was designed for computers when they were much smaller, so it's quick and tiny and works nicely over this kind of remote. Oh, now that's weird. Someone else is using the same port, perhaps? Well, that's one of the reasons that you might want to let it pick a port. I'm going to hop off that port and pick a different one. I've never seen that before, but that's what it looked like. I was in someone else's account. That's kind of scary.
Especially scary because I'm probably the last one to have run.
Huh. I mean, there is that danger when you're messing with port numbers and stuff. Okay, let's see here. All right. Okay. Oh, and this is actually starting the more scalable but still early access version of TotalView. Let's see here. I'm just going to start a separate one. Okay, so cd.TotalView cap blocks. Remove.tvdrc. Okay. Going to just do a Q sub. So that's all I needed to do to get a fast graphical connection to the Vesta system, and that would work just as well from wherever you go home to after this session as it would from here. It works really great over a low latency connection. Okay, I'm going to just do grep Q sub. I just don't remember the command off the top of my head, so I'm pulling it up out of my history here. I'm sure you guys probably have this all scripted. We ran anyways. Okay, so now, which directory am I in? Okay. This is the directory where I've got the testing, the lab manual, and we've got some programs and some sources in here, and an example TVDRC. I'm just going to go into programs. And for the first part of the demo here, I'll just run TotalView on my simple combine. This is just a simple demo program that will just show off some of the basic features of TotalView. So this is the TotalView user interface. We can just next and step and work our way through the code right here. Let's go in here and look at, for example, some objects. So if I just double click on cylinder, for example, this will tell me about a C++ class here called cylinder. We've got different information about the base classes and things like that. Close. We can, I'm going to run past that section here. If I've got an array, I can tell this that I've got 10 of these, for example. One of the cool things that TotalView, for example, can do is often in a C++ program, you might have scientific, especially a scientific C++ program, you might have things like this that are structs of, arrays of structs. And one of the things that you might want to do is you might want to look at the values of those structs all together. So I can just click here. I can say dive in all, and you can get an array of those elements. So this just shows some of the kinds of things that, little things that TotalView does to make it easier to see this kind of stuff. You can also hover over variables, which pop up with the value. You can see we've got your array values up here shown. You got all your breakpoints displayed down here. the different processes, the different threads that you're attached to. See, I really just wanted to show some very basic functionality with this. Okay, here, I'll get into an area where we get, this is just showing some visualization that we've got automated through an evaluation point. And if I go here next, we can show we're now in a parallel section of a code. It's as easy as clicking so I can see what's going on here. For example, arg, I can look at the arg structure across all the different threads and see what the values of that structure are like for each one of the different values. And I can run individual threads. So in the interface, you've got the go, next, step buttons and things like that. In a serial program, it's really simple, right? You've just got one point of execution. You can either run or halt, right? Fundamentally, in all of our parallel programs, you have lots of different choices. When you tell the program to run or halt, which one of the processes do you want to run? That's sort of one of the challenges of parallel debugging sort of conceptually. So in TotalView, to simplify things, we've got a box here so you can choose your focus around the thing you're looking at. It can be narrow or broad. Let me just choose a narrow scope here, and let me dive on a variable that will help me know where I am. For example, the J value is my index loop. I want to view this across all my different threads. And I can, for example, tell one thread to run around the loop separately from all the other different threads. Or I can tell the process and tell it to run. So now all the different threads ran around the loop. So this is actually another difference of between TotalView and a GDB-based debugger is we have the ability to set breakpoints that have different widths. So when you get to the breakpoint, and again, in a serial debugger, that's really simple, right? The program stops. In a parallel debugger, what do you want to have happen when you get to a breakpoint? Because you've got 10 different, you have 10 different threads of execution, or 100,000. They're running through the code. When one of them hits a breakpoint, what do you want to have happen? Trying to solve, you might want to stop just that thread, or you might want to stop the entire process, or you might want to stop the entire program to sort of see what everything is doing when any of them get to this point. So you have those options here in the thread breakpoint. So you can set a thread width breakpoint, a process width breakpoint, or a group width breakpoint. And group is just shorthand for all the different processes. In the CLI, you can define it more precisely. You could have it stop an arbitrary set of threads, for example. But here we've got it set to thread width, and that allows us to have a breakpoint in a loop. This happens to be p threads, but it could be OpenMP, and this allows us to see how each one of the threads executes as we go through our loop. So if we hit go, they all run. Each one of them separately runs to the breakpoint and stops. So it'll tend to synchronize things among your different threads. Alternately, you could set it to be process width, and then when any one of them, set this to be process width, when any one of them hits the breakpoint, it stops the entire thing. So now you see each one individually advancing, right? So we get to the breakpoint, it stops everything. In the other case, we ran everything, and when it got to the breakpoint, just it stopped, so all of them got to go around the loop once. Question in the back?
So what happens if you're stepping through on one processor and you hit a synchronizing communication? So just wait there until you individually make the other processors sync up?
Yes. Because the synchronization that's happening in the target, we're not trying to change the target program. You're taking control. So the control you're taking here is kind of like when you just let a program run, the operating system is choosing which threads get to run. You're taking that role. You can choose to run whatever sequence of thread operations that you'd like, or you can actually you can do if you do the process go, you kind of leave it up to the operating system. Does that make sense? So the synchronization that you might have in the program is all independent of this. That's actually important because what you might be trying to do in a troubleshooting scenario is trying to provoke, and this gets back to the sort of philosophy of debugging that David was going through, which was cool, is a lot of times, if the code was behaving as you expected it to, you wouldn't have a bug, right? So the code is behaving in a way you didn't expect, and what you're trying to do often in debugging is trying to drive it to that place that you didn't expect. But you still have the controls that you might have, like the thread synchronization constructs might be in your code. You want them to still operate the way they would normally, and ideally keep it from going to that sort of strange place. And so you want to be able to test that hypothesis with TotalView. And that's the kind of control we're giving you here. So we're not doing anything to disable any synchronizations that are in your program. Now you can go in, I guess if you had a sync threads or something like that, you could go in and write an evaluation point that skipped around the sync threads. So you can do tests like that as well without having to recompile. But fundamentally, the control you're getting here is the same as what's passed to the operating system when you let the program run. Make sense? OK. So I wanted to throw a little bit of, show a little bit of thread control debugging up there. That same concept applies to multiprocess. Let me now run a demo of an MPI program. So, and Ray had provided some great little scripts. Run TV. Oh, I got a semicolon there. Run TV, which I sort of modified slightly for these examples. v2.sh. Yes, probably. Hopefully the font on the TotalView side is reasonable. The font on the that was just running I was just running a script, so probably I can make the font a little bit bigger. There we go, large. Okay. So let me just let this. So I've just launched, and what I did was this was what was in the script is basically just a command line, which is a run job. So take the same run job command that you would normally use to run your program. Put TotalView in front of it. And actually, I think it's TotalView and then space dash dash args, and then your run job command. And then you basically don't change the rest of the command line. That's all just in a script. And again, there'll be some examples of those that you can work through this afternoon if you'd like. Let that run. TotalView is attached to the run job command itself. The run job command gets to the point where it becomes a parallel session, and then TotalView recognizes that and says, hey, would you like to stop the program now? The reason it's asking you this is if you say no and you don't have any breakpoints set in the application will just run away, which may be what you want. If you just want to run to a crash, that's perfectly fine. You can just say no here. If it's the first time you're debugging, you probably want to say yes. Then that gives you the opportunity to set breakpoints. I happen to actually already have some breakpoints set in this one, but I'll still show you the way that I would recommend doing it, which is to hit yes. Just take a second here for TotalView to synchronize all those processes. See the progress bar there. And again, this is the non-scalable. I'm just using the production version of TotalView at a relatively modest scale here. Looks like 2048 processes. So it's fine at that sort of scale without the optimizations that we talked about earlier. If I have time, I may be burning through all my time here, but if I have time or afterwards, we can demo it. It was running great at 32,000. I even ran one at 65,000 here earlier, last night, I guess. So you can do that if you want during your evaluation, or during this training here. So anyways, we got TotalView. You can see we're attached to all these different processes. And we can set breakpoints. It's as simple as just clicking. We did that before, I think. Hit go. That's again something that you can choose to take different directions. You could set the breakpoint only in a single process. And similarly to what we talked about before, you have the choice of when you hit the breakpoint, do you want to stop the individual process or do you want to stop all the processes that are part of the job? OK. I'm going to. You can again look at variables, dive on things. You can look at variables across all the different processes. Talk a little bit about MemoryScape in my last few minutes. One of the things that TotalView can do, I think, very well is give you a sense for where your program is using memory and help you troubleshoot things like memory leaks, memory array overruns, and things like that. This shows the graphical view. What this is giving you is a map of your heap memory in your program. So everybody mentioned they were doing C, C++. So you don't get the benefit the Fortran programmers have of not having to worry about the heap. You guys are solely responsible for making sure that you treat the heap carefully and don't, for example, create memory leaks. This is showing a demo program which is intentionally bad, so it's got all kinds of leaks. What you can do is bring up TotalView on your program, tell it you want to do memory debugging, run along, and then all you have to do is click on one checkbox here, detect leaks. What we can do is we can go through your program, look at all the different memory allocations, and then filter them into two buckets, one of which is the bucket of all the allocations for which there's still a pointer pointing to the allocation. And we can optimistically assume those are not leaks. You've done things well. You've still got a pointer pointing to it. The program could conceivably use that memory and clean it up. This can be done at any point in the program. The other bucket is the bucket of allocations where there's no longer any pointer pointing to the allocation. It's kind of like a garbage collection kind of pass. And I would challenge you how, if you don't have a pointer pointing to the allocation, are you ever going to go around, go back and clean it up? So this can allow you to detect memory leaks in your program, even if they haven't grown to be huge, even if they aren't dominating the memory yet. So we've got a built-in leak detection capability. We do this by interposing between your code and your malloc. We can detect all kinds of simple errors like double freeze. We can give you this graphical report. So we record all the allocations your program makes. The allocations are in green. When you deallocate something, it turns gray. And then when you reallocate, like this is reuse of a large block for subsequent smaller blocks. And then the white here is gaps between your allocations. So they're places where there hasn't ever been anything allocated. I talked about the leak detection. You can look for a memory corruption for writing past the end of an array, or maybe getting the size on an MPI send or an MPI receive wrong so that you're smashing some data structure. You can turn on these little guard regions around your code, around each one of your allocations or a subset of your allocations, and will trigger and tell you when those things get corrupted. You can also do comparisons. And I talked earlier about sort of optimizing your code. If you're getting into trying to understand where your program is using memory, this can be a really, really powerful tool. We'll break down the memory in your program, again, the heap memory, by source code or by program object, by source code file, by function, and then by line number. And we can diff that across any two experiments. So you could take two different ranks of an MPI job and diff them. You could take your program at an earlier point in execution and a later point in execution and diff them. You could take your program with two different data sets or your program at two different scales and see how the memory usage of different components. We've had customers who have had challenges, for example, as they tried to scale up their MPI library, the sort of size that it needed to keep different kinds of unexpected queues and things like that was exploding and taking up way more memory than they anticipated. So they were able to use this kind of tool to find that kind of behavior. You'll just have to look at the slides for stuff about accelerators and coprocessors. We've got some stuff about both the Xeon Phi and CUDA. Again, look at the slides for our batch debugging functionality and or talk to me. We've got some great functionality. It's very simple printf replacement that you can basically go in and say, let my program run, and then rather than going in and putting a print command in your program, you can just tell the debugger to print a particular variable. Why is that better? Well, we know all the symbol information, so we can print, we can sort of pretty print anything without you having to write the routine, and also we can do things like do memory checking in there, and fundamentally you don't have to recompile. The debugger can just do that for you. And talk to me afterwards for the reverse debugging. It's really cool. I was hoping to have a few minutes to demo it, but I spent more time talking about the philosophy of breakpoint setting than I anticipated. But come back and we can talk about this. This is not available on the Blue Gene, but available on any x86-based system, and it lets you basically run to your crash, look at the crash, go, hey, this value is crazy. How did it possibly get this way? And then not having to run, not have to start from the beginning and get back to the point where that value got the crazy value. Because it might be a needle in a haystack. It might be 1 of 10 million pointers went bad. So it's great when you have the bad pointer to just be able to go, okay, now how did this get this way? If you've recorded everything with Replay Engine, you can start from the bad pointer and just work your way backwards. Or whatever scenario, and work your way backwards. And we've captured everything you need to reproduce it. OK. So sorry to cover a lot of ground in a short period of time. Hopefully you appreciated that I did more demoing and less slides. If you want to try this yourself, here are the things I think you need to know. So just add plus TotalView in your .soft. That should have been a plus TotalView. Use this remote display client, and I can point you in. I should have put it on the slide here. You can go to the Roguewave website and grab that. Just add TotalView args before run job. So this shows what that looks like. So run job, block, Cobalt part name, P16, demo MPI, and I just add TotalView-args in front of that. If you want to try out the high scale functionality that I mentioned, where we use a tree, an MRNet tree, copy this file here into your .totalview.tvdrc. If you want to do memory debugging, which I talked about for a while, here are you have to, on the blue gene, you have to link either statically or dynamically with that. On x86 systems, we can dynamically interject the memory debugging, but on the blue gene, you have to do a little bit of link time work. And for the period of the training, we've got generous licenses on Mira, Vesta, Cetus, and Tuki. Note, Tuki's not quite set up yet, but it will be hopefully soon.